few questions waiting on the Socrative app today. The first one, these are review from our last class. First one here, the line spectra, also called emission spectra, the elements are blank to each other. So we found out they're different from each other. Very good. Next up, objects moving away from a stationary observer appear to have a blank wavelength as compared to the stationary observer. And of course we found out that was a longer wavelength because of course if we're moving away, that will take the waves and stretch them out. If we're moving towards each other, that's going to take the waves and push them together. Then we asked, what is the position of the woodblock that has the highest state of potential energy? Of course we said it was 6 feet off the ground. We compared that to the electron in the nucleus, saying that the further away that the electron was away from the nucleus, the greater its potential energy. An electron that is in the first energy level, that is closest to the nucleus, is said to be in, and that was called the ground state. Again, we called the ground state the lowest state of potential energy. And then finally, the Bohr model only worked well with the simplest element. In other words, it only worked well for, and that would be hydrogen. And why is hydrogen the simplest element? One electron, exactly. It's right up here in the periodic table. It is the simplest of all the elements. So it only worked well. Now, I don't believe we mentioned that, but that's one that certainly you should have been able to figure out from stuff we've covered earlier this semester. All right, so we're going to start by just looking again at the stuff we wrapped up the hour with on Tuesday. We talked about some uses of the line spectra, which we also called the emission spectra. We had some video clips of them. We made an analogy to the energy levels kind of being like the rungs on a ladder as being the only allowed levels. And of course the lowest level here being the ground state. And going up from there, we refer to that as an excited state. And that each color in the line spectrum corresponded to a different jump from the energy levels down to a lower energy level. Now, as we had there in our first set of questions on the Socrative app, we said it only worked well for hydrogen. And the biggest weakness that this model had at the time, there's actually a couple. One of them is that scientists were unable to describe this quantum leap. In other words, how could electrons go from one level to another level? And in doing so, they would have to not exist anywhere in between. So that jump had to be immediately done. Second one is that it only worked well for hydrogen, so it broke down when we looked at other elements. And then the third thing that scientists knew at the time is that when electrons moved in these curved paths, they gave off energy, and that didn't make a whole lot of sense because if they gave off energy, that means that they should continually be dropping down into the nucleus, and that wasn't happening. So we're going to have just a little bit more theory, and then we're going to show the results of that here in just a moment. Turns out that what we're talking about all came about to be described in an area of chemistry and physics called quantum mechanics. And quantum mechanics came out in the 1920s to help address some of these weaknesses in that Bohr model. And here were the main components of quantum mechanics that came about. First of all, there was a scientist by the name of Louis de Broglie. And de Broglie, he came up with a statement something like this. He said that electrons have a dual nature. Electrons have a dual nature. And that means that they sometimes behaved as particles, which of course makes sense, and they sometimes behaved as waves, which at that time didn't make a whole lot of sense, but de Broglie came up with this idea. Now the way that de Broglie arrived at this idea, this was about 1923, and again, we don't need to know names and dates in here, but just kind of putting things into perspective. De Broglie came up with this idea because at the time it was known that light had a dual nature. So if we're talking about the light coming down here, light has a dual nature. And in other words, light usually behaves as if it is a wave. And all waves go through the same types of characteristics. That is, they can be reflected off of surfaces. We know that light can be reflected off a surface. Just like if you dropped a stone in a puddle or whatever, you see that the waves spread out from there, but if there's a barrier, it's going to hit that wall, that barrier, and it's going to bounce back. And there's other things that light would do. For example, we're talking about waves. I don't know if any of you have ever been out in a boat near a cliff. I have been. And this was kind of one of those things where I had probably thought I was going to come close to losing my life. Was out in a boat one time on Lake Superior, and if you've ever been out there, you know that the waves on Lake Superior can get to be really big. And so this particular day they weren't all that big, but they were still 3 to 4 feet high. And if you're in a 17-foot boat, that is a relatively large set of waves. So that boat was rocking around. And any of you ever been up by the Fossil Islands before? Okay, so you know that there's sea caves and everything up there if you've been up there. And so what will happen is that the waves from Lake Superior will come in and they'll hit those walls by the sea caves, and then they start bouncing back. So what will happen then is that when they hit those waves and start bouncing back, those 3 to 4 foot waves then go through a process called wave addition. So instead of being just 3 to 4 foot waves, they wind up being 6 to 8 foot waves, because again they bounce off and they come back, and the thing is they become very irregular. And now if you're in a 17-foot boat with 6 to 8 foot waves and really irregular, that was one of those things, like I said, saw my life flash before my eyes. But the light does a whole lot of the same thing. When light strikes a surface and bounces back, and also go through wave addition, just like waves of water can. So we say that's a wave-like property. But light, it turns out, also has a particle-like property. And now again, we're talking about light, not the electrons. But light has a particle-like property, and we use it when we use these solar-powered calculators. When light strikes the surface on here, what happens is it causes an electron to be kicked out. If light keeps striking the surface, then those electrons keep getting kicked out of here, and it'll kick out enough of them such that it can generate an electric current that causes this calculator to operate. And that's a particle-like property, because in order to kick out things that have mass, then it also has to be something that is particle-like, something that has momentum that hits that surface that causes it to kick out. So de Broglie thought that, well, if light can have this dual nature, behaves primarily as a wave, but has some of these particle-like properties, and he thought, well, perhaps we've been looking at electrons the wrong way. Well, we think of electrons as particles because they're so tiny and because they move so fast. It turns out that they could have some wave-like properties. And that's exactly what de Broglie went on to prove. And the end result was the development of something called an electron microscope. So you and I today have heard of electron microscopes, but that came about because when we shoot paths of electrons or beams of electrons at small matter, very tiny things, it turns out it interacts with that matter as if it were a wave. And so that's what de Broglie came about and suggested. Then there was another scientist about this time whose name was Werner Heisenberg. Werner Heisenberg. And he developed what's called the uncertainty principle. But I am sure that some of you have heard about Heisenberg somewhere else. Where have you heard about Heisenberg? Some of you, I know you have. Yeah, where? Breaking Bad, exactly. In Breaking Bad, there was the character, Walter White. He was actually a chemistry teacher, just like me. But he wound up going into making meth. And he behaved in a very unpredictable manner. And so he took on the code name of Heisenberg because he behaved in a very uncertain manner. But the uncertainty principle that was developed by Werner Heisenberg in the 1920s went something like this. In fact, there was some mathematics that came about, and what it showed is that it was impossible to simultaneously predict the speed and the location of an electron. That's what the uncertainty principle says. It was impossible to simultaneously determine the speed and the location of the electron in an atom. Because if we learned something about its speed, then we wouldn't know anything about its location. If we learned something about its location, we wouldn't know anything about its speed. And so when we looked at the Bohr model of the atom, going back here, this was entirely too predictable. And so the uncertainty principle showed that that couldn't happen. Now, I can't show it to you in here. I mean, I could. But the mathematics that is associated with this is like multivariable calculus and differential equations, and I'm guessing nobody in here is that far yet in their math. Okay? So that would be like in your second and third year of math, college level math, if you were to take it. But again, the mathematics show that the Bohr model is too predictable. And then there was a third scientist at this time. His name was Erwin Schrödinger. And Schrödinger, he treated electrons as waves. And developed what is called the wave equation. Now, the wave equation is also something that the mathematics are way beyond what we can cover in here. But what we can do is we can look at the results of the wave equation. And what the wave equation wound up showing was this, is it defined orbitals. And these orbitals were given that name rather than orbits. To depict the locations of electrons in atoms. And we would define an orbital like this. We define an orbital as being a region in space where there is a high probability of finding an electron. And so what Schrödinger did is he really used the two ideas, the ideas of de Broglie, which talked about treating electrons as waves, and the idea of Heisenberg, which said that we can't tell exactly where electrons are located and their speed at the same time. We can only know one or the other. And so what I have up here is a number of different orbitals. And these here represent regions in space where there's a high probability of finding an electron. It doesn't tell exactly where they're located, but it's very probable in finding them in these locations. Now, here's some analogies that can be used. First of all, this here represents a bicycle wheel with spokes on it. And what will happen is if we took that bicycle wheel and we started spinning it around really fast, what would happen is that those spokes would wind up filling up a volume. And if we were to look at it, we probably wouldn't see those spokes spinning around in there, especially if it's going really fast. But we know they fill up the volume because all we'd have to do is just take a stick or something and pop it in there, and we'd find those spokes rather quickly. But the way they fill up the volume would kind of be like the way we talk about electrons in an atom. Those electrons are moving around very quickly, but we don't know really the details by which they move. So areas where we see it more darkly shaded is where it's more probable of finding an electron, and areas where it is less densely shaded is where it is less probable of finding an electron. And we can kind of make the same comparison by using a vibrating string. If we took a string and we plucked it, that string would wind up vibrating back and forth and would fill up a volume. And again, if we talked about the probability of where we might find that string at any moment in time, it might kind of be like comparing it to an electron and an atom, this here representing an orbital. In areas where it's more densely shaded, it's more probable. Areas where it's less densely shaded, it's less probable. And so we wind up showing an orbital, something like that, now three-dimensionally, looking something like this. And we don't know the details by which they move, other than we know that they move somewhere inside of there. But turns out that this is not the only way a string could vibrate. We could have a string that could vibrate in all sorts of different patterns. In fact, we could have a string that vibrates something that looks like this. Now, if we were to look at these string vibration patterns, and we were to compare these two string vibration patterns to each other, I know we have some people in music here. What is the difference between these two? How would these two sound compared to each other? How would this one sound here compared to this one here? Higher pitch, exactly. This one here has a higher pitch. And if you're not in music and don't know what that means, I'm not a great singer, but here's how this would go. If this was da, this would be da, da, da. So again, those would be examples of what we mean in pitch. It's not differences in volume, but difference in pitch. And now to use a physics term to describe that, and we also use it in music, is we would talk about their frequency. Which one of these two would have a greater frequency? One of the greater frequency is this one down here. It has a greater frequency because it vibrates faster. That means it vibrates more frequently. So this has a greater frequency. Now it turns out that if we relate this to physics, what we could say is this, is that the energy is directly proportional to the frequency. Energy is directly proportional to the frequency. Now we've talked, remember we said we were going to be using these terms directly proportional to and inversely proportional to throughout the rest of the semester. So if we say that energy is directly proportional to the frequency, that means as we increase the frequency, what happens to the energy? It increases as well, exactly. So a greater frequency corresponds to a greater energy. So it turns out that as we look at these orbitals then, turns out that energy depends on a couple different things. First of all, we say that the energy of an electron in an orbital depends on the size of the orbital and we can also say that the energy of an electron in an orbital depends on the shape of an orbital. So again, it depends on the size of the orbital and on the shape of the orbital. So let's first of all talk about why the energy depends on the size. And so we could go back to the Bohr model, even though the Bohr model isn't accurate. The Bohr model talked about orbits rather than orbitals. But if we went back to the Bohr model, if these orbits were further away from the nucleus, what would that do to the energy of that electron? Would it be greater as we get further away or lesser as we get further away? We found out the other day that it is greater, right? Because again, the further away that the electron is away from the nucleus, that means it has more potential energy. So the larger the size of the orbital, then the greater its energy. So if we come back to this here, when we talk about orbitals, again, the larger the orbital, the greater its size, the greater its average distance from the nucleus, and the more energy it has. So when we say that the energy of the electron depends on its size, a greater size means a greater energy because on the average it's further away from the nucleus. Then we can say that the energy of an electron in orbital depends upon the shape of the orbital. So as we go across here, we see we're starting with very simple shapes, and the shapes over here as we go from left to right get to be more complex. So if we went back to these vibrating strings, in which of these two strings would have a greater amount of energy? Which one again has a greater energy? The one on the bottom. The one on the bottom has a greater energy because we said, exactly, it's a greater frequency. Energy is directly proportional to the frequency. So as this vibrating string pattern gets to be more complex, this is a greater energy vibration pattern. Be just like comparing an orbital to this vibrating string. If we had an orbital this shape, that's kind of like comparing it to a vibrating string like this, whereas comparing an orbital with a spherical shape is like comparing it to a vibrating string like this over here. So if we were to compare these two orbitals right here, the one that has the greater energy would be this one over here, the one that's more complex. And if we had an electron between these two shapes, the one that has the greater energy would be this one over here. So again, there's two things that go into determining the energy of the electron. One is the size of the orbital. So again, the size of the orbital, larger orbitals have larger energy. And then the second thing that we would say is we compare shape. And so the one that has the greatest energy is the one that has a more complex shape. So then this goes back and say, well, how in the world does this help us get past this idea of quantum mechanics, or of the quantum leap, where we said that this was a big issue? Because again, when electrons are going through this quantum leap, they were immediately having to go from one level to another level, and they couldn't exist anywhere in between. Well, now, if what happens is that these spaces overlap with each other, in other words, if we can think of these now coming together and they are on the same x, y, and z axis, again, their shapes that overlap with each other, and if this one has a lower energy than this one does here, the electron is sitting ordinarily in its lowest state of potential energy and it absorbs some energy. It could all of a sudden be going from confined in this space to being confined in this space right here. But because the two spaces overlap, we don't have to worry about them not existing anywhere in between because, again, the spaces overlap with each other. The other thing is that the Heisenberg uncertainty principle says we don't know the details by which they move in there. So we know that they're located somewhere in that volume, but we don't know the details by which they move around, other than it's very highly probable to find them in that space. So again, if you undergo a transition from one level to another without not having to exist anywhere in between. And of course, once in a higher state of potential energy, they're not necessarily stable there. So what will happen is they could lose energy. If it loses energy, it can go back then to being confined to a smaller space or a less complex space. And so that's how quantum mechanics came about then, and how today we wind up explaining the line spectrum is that instead of moving in these circular orbits around the nucleus, we talk about them moving in orbitals, the details of which we don't know how the electrons move. So with that, are there any questions on quantum mechanics? Any questions that you have? Okay, now as you read through chapter 9, let's see if I can bring back the syllabus here. If we're looking through our syllabus, just reminding you that we aren't covering all of the sections in each chapter. So in section 9, we're only covering up through chapter 9, we're only covering up through section 9.6. And then when we go on to 9.7, you're only going to be responsible for the valence electrons. So the interpretation you would take from this is that in chapter 9, you are not going to be doing any electron configurations. So again, no electron configurations. And also no orbital diagrams. So if you see reference to these things here in any of the, I know some of you have asked before about those practice quizzes at the end of each chapter that are in your textbook. If there's questions about electron configurations or orbital diagrams, these come from sections that you were to have skipped. So we will not be doing that as a part of this class. So let's go on and see what you learned here from our stuff. We'll pull out our mobile devices again. And the first one here says, the energy of an electron in an atom depends on the blank and blank of the electron, in which are the orbital in which it resides. Select both of the correct answers. Get our answers locked in. We'll count down. 5, 4, 3, 2, 1. Great. On the size and the shape. Next up, an electron in an orbital has the most energy if the size of the orbital is. And we'll get our answers locked in. Count down. 5, 4, 3, 2, 1. Exactly. It's if it's larger. Larger orbitals have more energy. And number 3, an electron in an orbital has the most energy if the shape of the orbital is. We count down. 5, 4, 3, 2, 1. Very good. All right, so that's going to take us next to our periodic tables. So let's get our periodic tables out. We're going to be writing on these today. Anybody want a new one to write on? All right, 1, 2. Anybody else? Anybody else need one? And we're going to be writing on these today, filling them in. Last call. Yep. All right, so with our periodic tables, so this isn't a periodic table, let me get a periodic table. Here we go. Now the next thing we're going to be looking at here, and what we will be responsible for, is what we call valence electrons. Valence electrons. And where do we find the valence electrons? Of course, they're in the atoms. Are they on the inside or the outside? They're on the outside. If you talk about curtains, the valence is the thing that goes on the outside of the curtains. That's called the valence. And so we say that the valence electrons are the outermost electrons in an atom. And the reason why we look at the valence electrons and not the other ones is because the valence electrons are the ones that wind up dictating the way that elements combine with each other. And it should make most sense that it's the outermost, because those are the ones that are most, if we're talking about electrons being lost or gained, it's most easily the ones that are on the outside that are lost or gained rather than the ones on the inside. So to determine the number of valence electrons, what we do is we look at the group number. We can either look at the Roman numeral, or we can look at the last digit of the standard alphanumeric values. So as long as you can read Roman numerals, you're good. And we're going to talk specifically about the A groups, not the B groups. So if we look at the Roman numeral will tell us how many valence electrons an atom has. So elements here in group 1A will have 1 valence electrons. If they're in group 2A, they would have 2 valence electrons. Out here in group 6A, these would have 6 valence electrons. And this all holds up for all of the A group elements with one exception. There's one element that's an exception to it all. Anybody know which element that would be? That one element is going to be helium. And that's because helium only has a total of 2 electrons. So I can't have 8 valence electrons if it just has 2 to begin with. So helium is your one exception. Helium just has 2 valence electrons. All the rest of them here in group 8A have 8 valence electrons. So again, if you're looking at the A groupings, again, the A groupings, the Roman numeral will tell us the number of valence electrons. If you don't know how to read Roman numerals, then you look at the last digit of the value. So the last digit here in 2 is 2. The last digit in 14 is 4. That's going to tell us it has 4 valence electrons. Again, the only exception is going to be helium out here. As far as the B group elements, most of these here have 2 valence electrons. Sometimes they have 1. But you don't need to know which ones have 1. Just know that most of them here have 2. When I say most of them, that's like about 80 to 90% of them have 2 valence electrons. Sometimes some of them just have 1 valence electron. Okay, but we're not going to be working so much with valence electrons with these anyhow. Usually the ones we're going to be working with valence electrons are going to be out here in these A groups. Now the way that we represent these valence electrons is by using something called a Lewis diagram. And this actually goes by about 20 different names. And so I'm going to try to write down these 20 different names like this. I'm going to make 3 different columns. There's Lewis electron, and then we'll put dot in the second column, and in the third column we'll put the word diagram, formula, structure, and symbol. And the way that it works is something like this. We could pick out one of the words in the first column. The second column is optional, and we could pick out any word in the third column. And they all mean the same thing. So if I referred to something as a Lewis formula, that's the same as the electron dot diagram, or a Lewis dot symbol, or a Lewis structure, or Lewis dot symbol. Again, all of those mean the same thing. So pick out one of the 2 words in the first symbol, one or both actually. Then the word in the second column is optional, and then any word from the third one, and they all refer to the same thing. So if, as I speak about these things, if it seems like my vocabulary is inconsistent, it's because chemists have called them all of these different things here when we name them. But a Lewis dot symbol look something like this. If we had a generic symbol, we'll just call it a letter X. This represents a generic chemical symbol. What we do is we surround it with dots. And what is if these dots represent valence electrons, what is the most dots we would have to have? 8, exactly. So if we come back here, we'd have 1, 2, 3, 4. And the rules tell us when we write out a Lewis diagram, we place 1 dot on each side, and then we begin doubling up. So we'd have 1, 2, 3, 4, 5, 6, 7, 8. And so when we look at the positions of the dots, we have top and bottom, and left and right. And if you have just 2 dots, again, what can't you do? You can't put them together. You can't double them up. So if you're going to put 2 dots on it, where do those 2 dots go? Well, they could go here and here, or they go here and here. They could go here and here. They could basically go on any side as long as they aren't doubled up. So again, when we write 2 dots, any one of those, any location that shows 2 dots is allowed as long as they're not on the same side. So again, the convention is we place 1 dot on each side before we begin doubling up. And so we could have a total of 8 dots. When we have 8 dots, this is what we refer to as an octet rule. An octet refers to 8 valence electrons. Now, of course, there always has to be some exceptions. And there's one exception in all of these, and that is helium. Helium will just have 2 valence electrons, and we write out a Lewis symbol for helium. Helium is going to have a Lewis symbol that's written with its symbol shown with 2 dots, and in this case the dots will be doubled up. But in all other cases which show them with 2 dots, they would not be doubled up. The exception is helium. They would be doubled up, whether they're doubled up by putting them on the right or putting them up on the top or the bottom or the left hand side. All of those are equivalent. The reason why we double them up in helium is because both of them are contained in the same energy level, and that energy level can hold no more than 2. So when we write out those 8 dots around the outside, the reason why we're not doubling them up is because they reside in different locations within that particular energy level. So if we write them out then for the different groups, the elements of group 1A would have how many dots around its symbol? Just 1. Elements of group 2A would have how many dots? 2. Again, where you place those 2 doesn't matter as long as they're not on the same side. Elements of group 3A would have 3 dots. Elements of group 4A would have 4 dots with 1 on each side. Elements of group 5A would have 5 dots. Does it matter where we double up? No, as long as it's doubled up on one side. Elements of group 6A would have 6 dots. Elements of group 7A would have 7 dots. And elements of group 8A would have 8 dots. With the exception of helium, which has 2. And so helium would write then with its 2 dots something like this. So if we wanted to then show Lewis symbols, let's look at a couple of examples. Let's first of all look at carbon. If we had to look at carbon, if we had to write the Lewis formula for carbon, we put in C, and what would we do with the C? 4 dots around it, just like that. It's that simple. If we had to do it for calcium, right here, Lewis symbol for calcium would be Ca with 2 dots. And if we had to do it for bromine, we'd put Br with Total of 7 dots. And where do those 7 dots go? Well, 1 on each side, and then we double up. Does it matter which sides we double up on? No. So we could double up and leave the one on the right free, or we could leave the one on the left free, one on the top free. It doesn't really matter. So we use these Lewis symbols then to represent the elements. We're going to go into that with bonding. In fact, today half of you are going to be doing your lab in which you're going to be making Lewis symbols of molecules, and then you're going to be taking these symbols, putting them together throughout structures of molecules. In lecture, we're going to be doing some of that in here next week on Tuesday. So let's go ahead and see then on our last couple questions on the Socrative app. How many valence electrons would we find in one atom of phosphorus? How many valence electrons in one atom of phosphorus? Okay, we'll get our answers locked in. We'll count down 5, 4, 3, 2, 1. All right, that would be 5. Very good. And the next question. This generic Lewis symbol would best represent which element? So which element would best represent? Would this best represent? And we'll get our answers locked in. Count down 5, 4, 3, 2, 1. Correct answer here should be S, sulfur, because how many dots are there? 6 dots. Okay, any questions with these? Okay, we're going to wrap up here today with some demos. I brought out some elements that we're going to look at, and those elements are, and I'll get them on the dot cam so you can see them. They're these 3 elements right here. So we're going to look at some lithium, sodium, and potassium. Now, where do we find these on the periodic table? What do we call these elements? The alkali metals, exactly. These are the alkali metals. So we're going to look at some reactions of the alkali metals. I'm going to move these aside. Now, to do each one of these, I need to get some water in each of these beakers. And one of the first things we ought to notice about these is the way that we've stored these elements. And you'll see that the way that we have them stored, I'll open one of these up here, I'll set these aside. Open up the lithium, and you look in here, you're going to see that it looks a little wet on the inside. And the reason for that is because these here are stored in some mineral oil. Can you think of any ideas why we might store them in mineral oil?
Preserve them.
Well, in part to preserve them, yes. But what are we trying to preserve them from? Well, we're trying to prevent their exposure to oxygen, exactly. We're trying to prevent exposure to oxygen because it turns out that each of these elements is very reactive with oxygen in the air. It also turns out that they're quite reactive with water. So we try to keep them out of water, and by storing them under mineral oil, we prevent those reactions from happening. So I'm going to take one of these out of here. I'll take out this larger chunk of lithium and put it on here. And I'm going to zoom in on this a little bit, and maybe we'll turn on the lights here. Hopefully you can see this a little easier. There we go. And what I'm going to do with this now is I'm going to take, this here is a butter knife, and just so you can see that it's a nice dull butter knife, just put it here on my wrist. It's nice and dull. And I'm going to take this piece of lithium, and I'm going to take this butter knife and cut it. Now, what I'd like for you to pay attention to, first of all, again, you've seen how dull it is. I'm putting a fair amount of pressure on here. It's not doing anything to my skin. And we're going to demonstrate how easily each one of these is cut. Now, there's going to be a difference in how easy it is to cut them, so pay some attention to this here as I cut each one of these pieces. So I'll start with this first one. You notice I have to put a fair amount of pressure on this one, but I'm still able to cut it apart. And when I cut it apart, you should be able to see this metallic luster that's on the inside of the metals. And now that luster, as it's sitting here now, is beginning to disappear. There's a little bit of blackness, that's a gray coating that's beginning to form on the surface of the metal here. And so I'm going to go ahead and set this aside. In fact, I'm going to set all of these aside here so I don't accidentally bump them and knock them into any water or anything. And then I'm going to take this piece here and I'm going to cut it into still smaller pieces. We'll maybe cut it into 3. There's 1, 2, 3. And yeah, we'll leave it at that. And then what I'm going to do is I'm going to set this aside, and I'm going to take this beaker of water and put on top of here. Now, in order for you to see what's happening, I'm going to zoom out just a bit on this, and what will happen is that it gets a little bit darker in here because this iris on the camera will change in size a little bit. So we'll try to get it to autofocus on the surface here. And then I'm going to add to this, I'm going to add an indicator called phenolphthalein. Now, I don't know that you've used this in lab yet. Does phenolphthalein sound familiar? I think you'll be using this in your soap lab, and so that's probably coming up in another week or two. Phenolphthalein is a material that helps us distinguish between acids and bases. And when we have either an acidic or a neutral substance, like this is water coming right out of the tap, phenolphthalein is colorless, and when we have a base present, it'll turn pink. And just because I don't want anything potentially serious to happen, I'm going to place an explosion screen up here. We don't want anything to pop out of here. And I'm going to go ahead and drop in a piece of lithium. And let's watch and listen to what happens when I drop it in. If it comes off of there. No? So now you can see the lithium is kind of dancing around on the surface there. What else do you hear? You hear a little bit of fizzing. What's that telling us is happening? We're producing a gas. All right, so we're producing a gas. I'm going to go ahead and take another piece of lithium. We'll dump that in. And since I cut 3 pieces, we might as well put the 3rd piece in. There we go. So now again you can see the piece of lithium kind of sitting there. It's retaining its shape, it's just getting smaller and smaller in size. And we'll let it finish doing its thing here. All right. Next up, that was lithium. Next up here, we're going to have some sodium. So we'll bring this back out here so you can see the sodium. And we'll zoom in on it a bit. Now to get this one out of here, I can just go ahead and stab this one and pull it out. And again, we're going to go ahead and cut this, and I'd like for you to pay attention to how easily or difficult it is to cut. So we'll grab a hold of it. And notice now this one here, if you compare how easily it cuts, does this appear to be easier or more difficult?
Easier.
Yeah, this one appears a little bit easier to cut. It's a little bit softer metal. You can see here when I cut off a piece, we see that metallic luster, but that metallic luster is disappearing on the pieces a lot faster than it was with the lithium. And so I'm going to go ahead and place this back underneath the mineral oil, and we'll set this aside. And we'll set this aside again, and then we're going to go ahead and drop these into some water. Now this time, rather than putting the phenolphthalein in, just going to show you that the phenolphthalein isn't what's causing the reaction. We just use the phenolphthalein to give us a little color. So I'm going to zoom, just so I can see that. I'm going to go ahead and drop in some sodium. I'm going to cut this into probably 4 little pieces. Maybe, yeah, we better put it into 4. And we'll drop them in and we'll watch what happens when I do so. So we got this first one. Notice it's irregular shape. We'll drop it in. You see what happened to its shape as soon as I dropped it in? What shape are you seeing? A little sphere, yeah. Once I drop it in, turns into a sphere. The reason why it turns into a sphere is because it's melted. So that sodium now is molten sodium that's floating around on the top. So what do you suppose has happened to the temperature here? Well, it's gone up a bit. And I have one more piece to drop in. And just so you can see that the pink color, well, the reaction wasn't caused by the phenolphthalein, but we could still find pink. I can go ahead and drop in some of the phenolphthalein, and we see that we have that pinkish color that forms. And so this is telling us that we have a base in there, just like we saw in the first one, by the formation of a base. All right. So if we compared the speed, first one versus the second one, which one went faster? Second one went a little faster. In terms of softness, which one was softer? Second one was, all right? So the second one there being the sodium. So now we're going to go on to the potassium. Now to bring over the potassium, and we'll flip this over a bit so we don't see all that oil. There we go. And we have a nice chunk of potassium here. We'll place it onto here, and we're going to go ahead and cut off a piece of the potassium. what would you predict about the softness for this one? Even softer? Okay, let's see if this is the case. Grab a hold of it. This one slices just like butter. Okay, very soft metal in there. And the metallic luster is still there, but the metallic luster disappears very rapidly. So as we're looking at the metallic luster in its reaction with air, as we went from lithium to sodium to potassium, the reaction in each case was a little bit faster. Okay? And as we looked at the softness, went on down the line, each one got progressively softer. So let's go ahead then and try reacting this with some water. We'll go ahead and break this into some smaller pieces. Let's go ahead and cut it into 3. There's 1. Again, notice how easily this slices. It really is just like slicing butter with a butter knife. There we go. We'll set this aside. We'll bring our water up here. Should we do this with or without the phenolphthalein? With? Okay. We'll put in a little phenolphthalein. I'm going to try to block out some of that light. There we go. Put in 1 or 2 drops into there. And then we'll go ahead and drop in the potassium. Now, what do you think is going to happen with the potassium? More reactive, less reactive? More reactive, yeah. How about we turn off the lights for this one? Alright, we're going to turn off the lights. I need to leave just one bank along the side here so I can see something. And we'll drop this in. I got the one piece on the butter knife. Drop it in there. Whoa. And we'll drop in one more. And my last one. There we go. It looks like I have a piece stuck to my spatula. There we go. All right. So, faster or slower? Faster. Yeah. Now, I could keep on going down the line. If I went from potassium to rubidium, what do you suppose we'd find with rubidium? Even faster. How about softness? Softer, exactly. And so, this here is kind of the beginnings of where we have the periodic table. So I'm going to open up my computer again. Come on. There we go. So this here is the beginning of the periodic table. And if we come back to the periodic table, we're going to look at an example. Come on, one more. This right here is the original periodic table as published by Dmitry Mendeleev back in around 1870. So again, this was a periodic table published by a Russian chemist by the name of Dmitry Mendeleev. In about 1870. And Mendeleev was a Russian chemist, but what he did is he looked at things just like you and I observed right now. And that is, if we looked at what it is exactly that happened, we can write out a chemical reaction for what we observed. So we'll start first of all with lithium. And we'll see here now if we can write out a chemical equation. Lithium was a solid, so we'd put in S. It reacts with water, so we'd react it with H2O. Phase label, liquid. Now, when the product formed, it caused this water to turn pink when phenolphthalein is present. Remember, when phenolphthalein turns pink, that tells us we have a base in here. And the base that we produce, I know we haven't discussed these yet. Anybody have any idea of the base? It's going to be lithium hydroxide. So lithium hydroxide would have a formula of LiOH. And of course that lithium hydroxide is dissolved in water, so its phase label is aqueous. And then if we had to have one more product, what else do we see happening in here? We saw gas forming, okay? Now, I had to use the explosion screen in here, and the explosion screen was there because the gas we produced was explosive. It wasn't oxygen, it was hydrogen. Exactly, it was hydrogen. So just like we saw in day one in here, we saw hydrogen gas. Formula for hydrogen gas is H2. Phase label is gas. So then if we went through here and balanced this chemical equation, turns out we'd balance it with a 2, 2, and 2. And this, by the way, was a question on your last exam. You were given the words lithium. Some of you might have had potassium in there, or sodium. But we have a chemical reaction for what took place. And when we then went from lithium to sodium, instead of having lithium here, we would then replace it with sodium solid, meaning that the product we produced instead of lithium hydroxide would have been sodium hydroxide. And then when we went on from here, we no longer had sodium, but then we went on to potassium. And instead of producing sodium hydroxide, we would have produced potassium hydroxide. So now, this was something that Mendeleev, one of many, 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 many things that Mendeleev would have observed, to indicate that there are some elements that had identical properties. In fact, what Mendeleev did then is he took about 50 elements. If you look in this periodic table, there's about 50 elements that were known at the time of Mendeleev. He started arranging them in order of increasing atomic mass. And when he arranged them in order of increasing atomic mass, he found out that the elements repeated themselves about every 8 elements. And so if we look at his periodic table, we see lithium, sodium, potassium in here. We see beryllium, magnesium, and calcium. And specifically, the way that he listed them, now it's hard to see these formulas here, but this here, if we were to blow this up, this says R2O. R2O is the way he wrote this. This one here says RO. This says R2O3. Basically, when Mendeleev lined them up, he lined them up based on the oxides of these elements that were formed. And so these here represented the general formulas for the oxides that were formed. Now, it wound up being called a periodic table because to scientists, the word period refers to something that repeats itself at a regular interval. And so what happened then is that the chemical properties repeated themselves at regular intervals. Basically, every 8th element repeated itself in terms of chemical properties and the types of oxides that were formed. And so when Mendeleev arranged them, there were some interesting things that happened here. For example, when we look at calcium and then skip on over to titanium, there was a hole in here. If we look at something like zinc and go over to arsenic, looks like there were a couple holes in here. What do you suppose these holes represented? Well, if this is in 1870, these represented elements that had not yet been discovered. So turns out that when Mendeleev published his periodic table, at the time, again, there were only about 50 elements. What Mendeleev was able to do with this was then predict the properties of elements that had not yet been discovered. Once those properties were predicted, within like 10 to 15 years, we discovered about 20 more elements because of the predictive capability of his periodic table. The other thing that's fascinating about this is that Mendeleev published his periodic table in 1870, and turns out that when we look at the periodic table today, we arrange them in much the same way that Mendeleev did, that is, arranging them by groups. But today, when we find them in a particular group, they're arranged that way based on their number of valence electrons. So at the time, Mendeleev knew nothing about valence electrons. The valence electrons didn't come about until the 1920s. So it was over 50 years later that the whole idea of quantum mechanics came about, and where we learned about valence electrons and such. And that's when Mendeleev's periodic table is explained why they are the way they are. So Mendeleev was way ahead of his time, but he arranged them based on their chemical properties. And so today, when we talk about the periodic table, what you are expected to know is that elements in the same group have similar chemical properties, just like we observed here today. But not only do they have similar chemical properties, but elements in the same group have the same number of valence electrons. So with that, I have a couple of things. First of all, any questions? Any questions on these? All right. So here's a couple of stories to wrap things up. First of all, before I tell the story, I want to show a video clip. This here is some sodium that was taken to a large lake in Washington State. This is 1947. Now, we don't do this anymore. You're going to see why we don't do it. But after World War II, there was tons and tons and tons, literally thousands of tons of leftover sodium from World War II that had to be disposed of. And here's what they did with it.
Pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Quite do that anymore. But I have a couple stories of my own. One of them here has to do, let me put the periodic table back up here. One of them was when I was in grad school. I started grad school in Mankato, and when I got in there, one of the things they did with all the grad students is they took us to the back room and they showed us all of the old chemicals in there. There's a bunch of old bottles in there where labels had fallen off, and it was going to be up to us students to identify what was in those bottles to make sure that they got sent off and disposed of properly. So we came to this container that somebody had looked at before and had not disposed of it, but had put the letter P on there. So of course, being the bright chemists we were, we looked up the disposal method for P, and these were these white sticks. If you look up the disposal method for P, it says the plate sticks under water and sends in an approved landfill. So we took these white sticks, we put them under some water, this was in the hood. All of a sudden these sticks, the flakes started coming off of there and started bubbling. Somebody realized that we were probably in big trouble, grabbed the explosion screen, and it wasn't the one like this. This is flimsy. We had one that was like bulletproof glass, set it down in front of there. About the instant it was set down, the thing exploded, cracked the glass, and we realized that we weren't dealing with P, but rather we were dealing with K. Somebody had mislabeled the bottle potassium with the letter P on there. So when we talk about your atomic symbols, it's important that you, of course, mind your P's and K's, right? Now the second one, this one was even more interesting to me anyhow. I started my career teaching high school, and one of the things I had to do was teach 9th grade science. Worst experience of my entire life, my entire career, I should say. And so we, however, had some sodium that we were demonstrating. We didn't have the lithium, sodium, potassium. We just had some sodium. And there was one of my colleagues who had a student that had seen the same thing, was very fascinated by it. Now, you saw how much I demonstrated the sodium, right? Just kind of like pea-sized chunks. We saw what large amounts of sodium do in there. Well, this student of his was very fascinated by it and wanted to know what would happen if I took this chunk. It's probably the size of a stone, about yay big. What would happen if I take this chunk and throw it in the snowbank? Okay, so he went into the stockroom, stole a chunk of sodium, put it in his pocket. Well, as you can imagine, when you put it in your pocket, if you're like a 9th grade boy, very devious and stuff, all of a sudden you start getting very nervous. When you get nervous, you start to sweat. Of course, sweat contains water, right? And so it's sort of reacting with the sodium in his pocket. Now, as you're going to learn in your lab here a couple weeks down the road, when we combine, just like we did right here, when we combine sodium with water, we wind up forming sodium hydroxide. And sodium hydroxide is commonly known as lye. Okay? Now, lye, it turns out, if you know anything, lye is used in the manufacture of soap. And you're going to be doing a lab here in a couple weeks where you're going to be combining lye with fat to make soap. Of course, not as only does your skin have some water when you sweat, but your skin is also full of fat. So it turns out that lye that was forming on the surface of that started reacting with the fat in the skin, producing soap. The process is very painful, by the way. So he went to where all little boys dispose of evidence, which is toilet. Threw it in the toilet. The bowl on the toilet exploded, and that is the end of the story. So, anyway, that's why protect your stuff. Don't play with sodium. All right, have fun. We'll talk to you later.